Hi everyone, my name is Fengnian from IBM Research. Today I'm going to tell you graphing for future electronics and photonics. So first I will start with what is graphing and why graphing is important. Graphing basically is a single layer of carbon atoms assembled in a honeycomb lattice, and it is the basic building block of graphite. So it has lots. The reason we are working with that because it has lots of very impressive properties. First is the electrons in the graphene can move very fast, and it's also very highly conductive, and it's atomically thin. And for photonics and graphene, it also interacts with photons very strongly in a very wide wavelength range, and it's chemically stable. And one most important thing I want to emphasize is, unlike other new materials right now, graphene is already can be produced in a very large quantity. Here I show a graphene on an 8-inch wafer. So we can envision a graphene integrated electronic and photonic circuits completely on a single on a single chip. So, however, despite of all these impressive properties, there's one problem in graphene, which is graphene is a semi-metal. As we all know, our information technology is based on the semiconductor industry. So if we want to make graphene more useful, we have to turn graphene from a semi-metal to a semiconductor. The reason is also very simple. For example, if you want to make a transistor, you want to turn it on and off. So in order to create a very solid, a nice off state, we have to rely on the band gap of a material. And for example, for photonics, if you want to make a light emitting diode, the first thing you want to ask yourself is about the wavelength of the diode. So in that case, the wavelength of the light emitting diode is determined by the band gap. So it's highly desirable to turn a semi-metal graphene into semiconductor while at the same time maintaining its intrinsic nice properties. Okay, so here's the method I come up with. So instead of using one single layer of graphene, here we use two layers of graphene. By applying an E-field in vertical direction, a band gap can be created. Basically, this is a more or less known approach. However, for 4 or 5 years, people are not able to do that because they are not able to make the right gate dielectric. So my innovation involves the fabrication of the bilayer graphene transistor with a novel gate dielectric. By adding a polymer buffer layer between the metal gate and the graphene, we are able to preserve the intrinsic property of graphene, and and while a band gap is created, the lots of nice properties are maintained. So using this approach, we are able to reduce the transistor off current by a factor of 30, which means we can reduce the power consumption at off state roughly by a factor of 1,000. And at the same time, we also made some bilayer graphene photodetectors, which allows us to detect 10 gigabits per second photo bit stream. So here I show the IDAM here. So in summary, I showed you that graphene, an atomically thin carbon material, has great potential in future electronics and photonics. And although the graphene is a semi-metal, it can be engineered into a real semiconductor, greatly improving its future in electronics and photonics. And if you have further questions, you can drop me an email. Thank you very much.